Maybe you know. Science meets the questions you never thought to ask. In 1980, a Harvard physicist named Sidney Coleman sat down to write a paper with a colleague, Frank DeLucia. The math was clean. The conclusion was not. They proved that empty space, the nothing between stars, the vacuum inside your lungs right now, might not actually be stable. Somewhere in the observable universe, a bubble could already be expanding at the speed of light. And if it is, you would never see it coming. You would never see anything again. To understand what Coleman calculated, you have to throw away what empty means. In the 19th century, physicists thought a vacuum was just absence. Pump the air out of a jar, and you have nothing. Then in 1948, Hendrik Casimir, a Dutch physicist working at Philips Labs, predicted that two metal plates placed a few micrometers apart in a perfect vacuum would be pushed together. Not by air, by the vacuum itself. The experiment was confirmed in 1997 at Los Alamos. The force was real. Tiny but real. Empty space, it turned out, was not empty. It was humming. Quantum fields stretched through it. Particles flickered in and out of existence in trillionths of a second. The vacuum had energy. It had structure. And here's the question that kept Coleman awake. If empty space has energy, how do we know it has the lowest possible energy? How do we know our universe is actually sitting at the bottom of the hill and not perched somewhere on the slope, one quantum nudge away from rolling down? In a 1977 paper, Coleman started building the answer. Imagine a marble resting in a bowl that sits on top of a taller hill. The marble looks stable. Nudge it gently, and it rolls right back. But it isn't truly at the lowest point. The real bottom is far below, at the base of the cliff. If something gives the marble enough kick, or if it just tunnels through the wall, which quantum particles can actually do, it falls. And once it falls, it never comes back. Coleman called the marble's first home a false vacuum. The real bottom, a true vacuum. Now scale that marble up to every cubic centimeter of space in our universe. If our vacuum is false, somewhere out there, in some random patch of nothing, a quantum fluctuation could trigger a tiny region to drop to the true vacuum. That region wouldn't stay tiny. It would expand. The boundary between the old vacuum and the new one, physicists call a bubble wall, would race outward at almost the speed of light. And inside the bubble, the laws of physics would not be the laws you grew up with. Here's the mechanism, stripped down. Every particle you're made of, electrons, quarks, the protons in your bones, gets its mass from something called the Higgs field. The Higgs field fills all of space. It was the discovery that won Francois Englert and Peter Higgs the 2013 Nobel Prize, after CERN finally detected the Higgs boson in 2012. Think of the Higgs field like the depth of an ocean. Particles moving through it feel drag. That drag is mass. Now, imagine the ocean has two possible depths. The one we live in, about 246 gigaelectronvolts, and a deeper one much, much further down. We're floating on the shallow shelf. If a tiny bubble of the deeper ocean forms, the water around it rushes in to match. In the bubble, the Higgs field is stronger. Electrons would be heavier. Atoms wouldn't hold their shape. The chemistry that builds your DNA, your neurons, the screen you're looking at, none of it would function. Not destroyed, just impossible. A new universe inside a wall, growing outward at light speed. But here's where it gets strange. You might think, okay, terrifying, but at least we'd see it coming. Astronomers would spot the bubble approaching. We'd have warning. We'd have time. We'd have nothing. The bubble wall expands at essentially the speed of light. Light is also what carries information. Every photon from a star, every signal from a phone tower, every image hitting your eye. Which means the wall arrives at exactly the same instant as the first hint that it's coming. There is no early warning system that physics allows. If a bubble formed in the Andromeda Galaxy tomorrow morning, 2.5 million light years away, the photons announcing its existence and the wall itself would hit Earth simultaneously 2.5 million years from now. You wouldn't feel pain. You wouldn't see a flash. The atoms in your retina would stop being atoms before the signal reached your optic nerve. In Coleman and DeLucia's own words from 1980, this would be the ultimate ecological catastrophe. Then they added a darker line. One's life, one's friends, the human race are all snuffed out. A physics paper had become an obituary. For decades, vacuum decay was a thought experiment. Then the Higgs boson actually showed up. On July 4, 2012, CERN announced the detection, a particle with a mass around 125 gigaelectronvolts. That number mattered. In 2013, a team led by physicist Joseph Lukin at Fermilab and another at the University of Helsinki ran the calculations. They plugged the measured Higgs mass and the top quark mass, about 173 gigaelectronvolts, into the equations that govern vacuum stability. The verdict came back the same from multiple groups. Our vacuum is not stable. It is what physicists call metastable. We are sitting in the bowl on the hill. The bottom is still down there, somewhere. A 2018 paper by Andreas Anderson, William Frost, and Matthew Schwartz at Harvard refined the estimate of how long, on average, our patch of universe should last before a bubble nucleates inside it. The number they got was 10 to the power of 794 years. That is a 1 followed by 794 zeros. Astronomically safe, cosmologically certain. The vacuum will eventually decay. The only question is when and where the bubble appears. And just when you think we've figured out, the math turns on us. That number, 10 to the 794 years, is an average across our entire observable universe. It assumes our laws of physics are complete. They aren't. We don't know what dark matter is. We don't know why the cosmological constant has the value it does. We don't have a theory that joins gravity to quantum mechanics. Any one of those unknowns could shift the calculation. Worse, in 2015, physicist Anders Anderson and others noted that black holes might catalyze the process. A microscopic black hole evaporating somewhere in deep space could, in theory, act like a seed crystal, making a bubble nucleate near it billions of times faster than empty vacuum would on its own. Stephen Hawking himself, in a 2014 lecture at Cambridge, warned that the Higgs field could become metastable under certain conditions, and that a high-energy event could trigger catastrophic vacuum decay. He clarified later that no Earth-built collider could do it. The galaxy, however, is full of natural events that exceed anything humans can build. Cosmic ray collisions, neutron star mergers, black holes feeding. Right now, as you breathe, the Higgs field is humming through every cell of your body. The vacuum between the atoms of your hand is not nothing. It has a value. That value, according to our best math, is not the lowest it can go. We are guests in a metastable house. The good news, the calculated lifetime is so vast that the heat death of the universe will almost certainly arrive first. Stars will burn out, galaxies will drift apart, even black holes will evaporate before our patch of vacuum is statistically expected to fail. The bad news, expected, is the key word. Quantum events do not respect averages. A bubble could nucleate in 10 to the 794 years. It could also nucleate before you finish this video. The probability is unimaginably low. It is not zero. And if you want a quieter thought, consider this. Some physicist alive today, working at CERN or at Fermilab or at a university you've never heard of, will publish a paper that revises this number. Up or down. Vacuum decay is not science fiction. It is an open homework problem. Sidney Coleman died in 2007. He never saw the Higgs boson confirmed. He never saw his 1980 paper become a serious calculation about the actual fate of our universe. But somewhere in his equations, that bubble he imagined is still waiting, not as a metaphor, not as a doomsday fantasy, but as a number, a real number, sitting on a real graph, plotted against the real mass of a real particle that physicists found in a tunnel under the French-Swiss border. The vacuum inside your lungs right now is the same vacuum Coleman wrote about, the same one that might, somewhere far away, already be peeling open. You would never see it coming. You would never see anything again. 47 years after that paper, we still don't know if the bubble exists. We only know that, mathematically, nothing forbids it. Next time, we go inside the strangest object physicists have ever modeled, a black hole that doesn't just trap light but might be a doorway. There's a theory, taken seriously by people at Princeton and beyond, that every black hole births a new universe on the other side, which would mean ours wasn't born in a Big Bang. It was born inside something else. Subscribe so you don't miss it. Thanks for watching. If this sparked a question, drop in the comments. It might be our next video. We'll see you next time.